Hello everyone, welcome to my presentation. I am Priya Shanmugasundaram and today I'll be discussing about NAR-miner, discovering negative association rules from code for bug detection. What is this paper solving? Let's start with two questions. Buggy software code is everywhere. Is there a way we can avoid having to manually look for bugs and potential violations? The second question, is it possible to obtain solutions for different kind of bugs, even corner cases which occur rarely? This paper answers these two questions. Let's look at the question one first. Yes, it is possible to avoid having to manually look for bugs and violations. How do we do it? Through data mining. These techniques can automatically extract programming rules by identifying underlying patterns in the code. Let's delve a little deeper. Traditional methods for finding bugs rely on predefined detection rules or known vulnerability patterns, and these methods only work if the vulnerabilities are already known. A new approach called code mining is proving to be highly effective, and how it works is it learns implicit programming rules by analyzing the structure of the software and finding underlying patterns in the code. If a piece of code violates the learned rules, then it's most likely a bug or a security vulnerability. Most previous research on using code mining to detect bugs focuses on positive association rules. A positive rule is written as A double arrow B, which means that if an action A happens, then an action B should also happen. So for example, if a function allocates a memory through a process A, then it should free the memory through a process B later. These should be occurring together. These should be occurring one after the other. They are positively associated. Unlike positive rules, negative association rules indicate that two actions should not occur together. So they use the association mining to infer programming rules, which can then be used to detect bugs in an automated fashion. But they study the negative association rule mining part of code mining in this paper. So, for example, if a function frees a memory using freenetDev, it must not free the same memory again using kfree to prevent a double free bug. And double free bug, as we know, results in a lot of crashes and it can be a vulnerability to the system. So it is quite important but often overlooked in literature, negative association rule mining. And that's why this paper delves deeper into that. Now coming to a overall high level workflow of how code mining works. So firstly, the source code is converted into a structured format, which can be an item set or a graph, which basically represents the different elements in the program and the relationship between the programs. And in the second step, data mining algorithms are used to sort of analyze these structures and extract the underlying patterns. And finally, these underlying patterns are used to form rules, which are then used to detect rule violations, which identify bugs. So coming back to the second question, is it possible to obtain solutions for different type of bugs, and how about corner cases? So firstly, yes, it is possible to obtain a solution for different kind of bugs because this particular solution relies on data mining, which does not require you to have a knowledge of all the vulnerabilities. And second thing is it also covers corner cases because negative association mining is especially good at capturing rare but serious bugs. The paper uses negative association mining to help identify serious bugs such as memory corruption, crashes, or security vulnerabilities. So why not positive rule mining? Why are we discussing so much about negative rule mining? The authors introduce a real-world example from the Linux kernel to show how their method works, right? So the function labbet new device is used to create a network device. It calls this function allocnetdev to allocate memory for the device. And the function netdevpriv retrieves the private data associated with this network device. And the private data is then stored in a variable called labbet. The memory allocated earlier by the AllocNet device includes this private data. The variable lap width holds reference to, let's say, the part of that allocated memory. So if something goes wrong in line 11, then the memory needs to be freed. So in line 21, if you see, they use freenetdev and they free the ndev memory first. And in line 23, they use kfree and free the lapbeth afterwards. The sequence of the memory operations is important. If, for example, if the memory is freed incorrectly, it can cause serious errors, right? Like the double free bug that we discussed earlier. So the same memory is freed twice, once by freenetdev and once by kfree. And this results in a double free bug. So let's see if traditional methods or positive rule mining can capture such a bug. So now that we saw this particular bug, traditional bug detection tools were used to sort of come up with whether it's able to find this bug. And they saw that it was struggling to find this bug because the Linux kernel itself is quite huge and the bug depends on the application logic, which is not very easy for the traditional method to generalize and understand. And coming to positive rule mining methods, like for example, NAR-miner. NAR-miner is a tool that mines positive association rules in the source code. And it found that around 85.6% of the cases that it had seen, allocnetdev is followed by freenetdev. And very few cases have a case where freenetdev and kfree occur together. So this suggests that kfree should not follow freenetdev and it's sort of an anomaly, right? But since antminer focuses only on positive rules, it only looks into expected behavior. So as long as expected behavior is met, it does not um, question an anomaly. The bug does not violate any positive rules per se, so antminer does not flag it. So even though the bug exists, antminer wrongly assumes that the code is correct. So this is one of the cases where positive rule mining is not able to catch a serious bug, which occurs quite rarely. So now let's look at what are the key novelties that are there in this paper, which make it a good contribution, and also how they solve for the uh, related work issues that are faced by related work. So the key novelties in this paper are twofold. The first thing is the use of a semantics constrained mining algorithm to focus the rule mining on elements which have strong semantic relationships. And the second thing is the authors introduce an information entropy to rank candidate negative rules and highlight the interesting ones. Sounds like a lot of jargon, but we'll get into each of these in detail and try to understand it. So the first challenge that they face with negative association rule mining is the rule explosion. So a major challenge in discovering negative rules is the rule explosion problem. When extracting negative rules, many of them do not actually help in detecting bugs. Most of them are uninteresting rules that lead to false alarms, and the it actually increases time for the developers in trying to fix false alarms while they could have a lot of time saved by working on something that is a real serious bug. So mining positive rules is simpler because frequent patterns are easy to detect, but negative rules involve rare conflicts, but this also imposes this additional layer of challenges which sort of picks up a lot of excessive rules. So this is one challenge that negative association rule mining has. So to solve this, they come up with the semantics constraint mining, which basically is instead of mining all the possible rules, the paper proposes to only consider function pairs which have strong relationship, semantic relationship, or strongly related to each other. So if a function, for example, allocates memory, the tool will only check other functions related to memory management. It will not check a function that is not related to memory management. So this will help it to avoid false alarms and also create a better mining algorithm. Now coming to information entropy. Information entropy is used to measure how general an API is. So higher entropy means it's a more general function, like a printk function, and a lower entropy means it's a more specialized function, like in a LockNet dev or whatever. So what they are trying to do is that to make sure the rules are very useful, the rules that they generate, they only look for rules which are very interesting or which have lower entropy or higher entropy rules are removed. They use it as a filter and they only look at rules that have lower entropy, helping them focus on more negative, meaningful rules. So now that we've looked at the two main things, which are the key novelties or the conceptual novelties in this paper, let's go one level deeper and understand how it works, how NAR-miner works. So from a high level, the workflow of NAR-miner is that first there is a data preparation stage where the source code is transformed into, let's say, the program elements, the relationships are extracted, and then it's stored into a transaction database. And then the transaction database is mined or analyzed one function at a time to sort of come up with these item sets which are separated into frequent and infrequent item sets. And then the negative rules are inferred from these item sets, which is then used for detecting violations or bugs. So now let's go into the data preparation stage, which is the first stage. So the study focuses on two key programming elements. So the first thing is function calls, and the second thing is condition checks. So like the if statements and everything. Two program elements are considered related if they share data, but there are two kinds of relationships that can happen due to data. First thing is data dependence. So if an element depends on a value computed by some upstream element, then those two elements are related by data dependence. Second thing is data sharing. If both elements use the same data within the same execution path, then they are sharing data and they're related by data sharing. And what this data preparation stage does is that it tracks how the data moves through data flow analysis and also uses this data flow analysis to sort of identify relationships between these elements. First of all, it identifies the elements, then tries to find out the relationship between the elements, and then uses data flow analysis to track the movement of the data. And then this is all combined and stored in the transaction database. Now moving to the next step, which is sort of a code processing step, where the NAR-miner uses the GCC compiler to understand the program structure. It extracts the control flow graph and also sort of the intermediate representation. For example, if you see in this image, so there's this code and it shows that the original source code and then the simplified form or the SSA form, which is used for the data analysis, where it sort of it analyzes the dependencies, right? It sees is valid, foo, and bar, they depend on the value computed by read to here, right? And is valid and foo are on the same execution path, so they share the data. And foo and bar are not connected, so they do not have any semantic relationship with each other. So it sort of generates all of these relationships and looks at the structure of the program. And then this SSA form is transformed into a database itself to prepare for rule mining. And each function in the program becomes one separate transaction, and the transaction has two things. So the first thing is the elements, which is the function call and the if statements and everything, and the relationships between them, like the data dependence or the data sharing sort of relationship between them. So each transaction represents a function, and each function has these two variables or these two attributes to it. One is the program elements, and second is the relationship between them. This is how it's being stored in the transition database. Now, how do they store the semantic relationships? So before storing the elements in the database, first they are standardized. And each pair of related program elements is stored as a tuple. So instead of storing the function names as text, what they do is they are converted into unique numbers. And if you see in this graph, um, each of the variables are the functions, or the statements are the nodes here, right? And the edges sort of tell you the relationship between the elements. So whether it is a data dependence relationship or a data sharing relationship is shown through these arrows. And then these are all converted to integers. Each of the nodes are represented by integers because integer comparisons are faster than text string comparisons. And this improves the performance when mining for patterns also. Now coming to extracting item sets. So traditional data mining algorithms only count, or like they are only dependent on the frequency of how often items appear together, and they do not consider the meaning of the relationship between the elements or anything of that sort. So what they would result in is a lot of useless rules, and they would also ignore the semantic relationships, right? And the paper also calls out that there is no existing algorithm for perfectly mining negative programming rules. So a new algorithm is needed. So they come up with a new way to sort of extract these item sets. So the first thing is they filter out uninteresting items and then uninteresting rules, and they only consider elements that are semantically related. And the algorithm only selects the function pairs that truly interact with each other. So for example, a good item set would be a alloc netdef function and a free netdef function. They share memory allocation responsibilities, right? But a bad item set would be a printk function and a free netdef function. They're not related. So they use an a priori algorithm which applies sort of a bottom-up approach, um, because it starts with small frequent item sets and then gradually builds larger patterns. So based on the a priori algorithm, what they hypothesis is that any subset of a strong semantically related item set is also strongly semantically related, because any two elements in the subset must be related in semantics. So in our case, if, for example, alloc netdev, free netdev, and k-free are semantically related, then alloc netdev and free netdev must also be semantically related, and free netdev and k-free must also be semantically related. So how the algorithm works? So the algorithm takes two inputs. So one is the minimum frequency support, and the second is the maximum infrequency support. So minimum frequency support is nothing but how often an item set must be appearing to be considered frequent. And maximum infrequency support is how rare an item set must be appearing to be considered infrequent. And if a function pair appears often, it's frequent. If it rarely appears, then it's infrequent, right? So the algorithm then categorizes the function pairs based on these thresholds, based on these MFS and MAS thresholds. And then it computes the support. Support is basically how many times an item set appears in the data set. So uh, if a function pair appears in a transaction, then the algorithm sort of counts it up. The counter increases. And a function pair is valid if and only if both functions exist in the same function. They have a real relationship. They have some sort of data relationship between them. So then these are considered as a transaction with a particular item set, right? So once we have extracted these item sets, next step is inferring the negative association rules. So a straightforward way to identify negative association rules is find all the infrequent item sets, the ones that come very rarely, and split them into two non-overlapping parts, A and B, and then use some measure like confidence to see how strongly A excludes B. And higher confidence means A almost never appears with B. Lower confidence means A sometimes appears with B. So this is how you can naively come up with negative association rules. But if multiple rules lead to same violation, then storing all of them is redundant. Second thing, for let's say we have an infrequent item set with like 5 elements, right? Then you can come up with around 2 to the power 4, 16 rules, but not all 16 rules will be useful to us. So this is a rule explosion problem again. So to address this, they come up with a way to infer interesting negative association rules. So a negative rule is only valid if its reverse rule is also meaningful. Otherwise, it's considered a false positive. That's what they propose. So what they do is instead of ranking just by confidence, they come up with another metric called interestingness. So where interestingness is nothing but confidence over the entropy. And the entropy of a function is given by this formula, which sort of tells you um, how how often number of function call instances and the probability of the function call appearing in different contexts. Like how many times, how many different contexts is it coming in? That's sort of what the entropy tells you. So the steps for this algorithm are: first, find the rule with the lowest confidence for each infrequent item set. Then you compute the confidence. Then you filter out rules with lower confidence and rank the remaining rules using the interestingness values. And from those ranked values, you output the top ranked rules for your bug detection. So this provides like a set of ranked negative rules that highlight rare but critical function conflicts. And this can be used to identify potential programming errors with fewer false positives, right? So now that was a lot of information. So just to put it in a 4-step or a 5-step summary, first, NAR-miner converts source code into transactions based on the program elements and the relationship between them. Then it extracts frequent and infrequent item sets based on how often they appear together or do not appear together. Thirdly, it uses a semantic constrained mining algorithm, which sort of filters rules that have lower confidence, which are rare, but have no sense or do not make any sense, or filters rules that have a high chance of being false positives. So how does it do it? It uses confidence and information entropy to come up with the interestingness measure through which it filters. And then you apply the information entropy to highlight the interesting rules. Then these rules are used to detect the violations, which could be potential bugs or security vulnerabilities. So looking at the experiment setup, the NAR-miner was implemented as a prototype to detect bugs in large-scale C programs. So they have a primary evaluation done on the Linux kernel, and they have around 15.5 million lines of code and around 376,000 functions. So to verify the NAR-miner's applicability beyond Linux, they also look at large-scale systems like PostgreSQL, OpenSSL, and FFmpeg. And three key parameters were set. So the first was the minimum support for frequent item sets. The MFS was set at 15. The maximum support for infrequent item sets was set at 5. And the minimum confidence threshold was set at 85%. And they look at 3 different versions. So first is the NAR-miner minus minus, which is the baseline version, does not have a ranking by confidence or a semantic constraint. The second is the NAR-miner minus, which adds semantic constraints to filter the weak rules. And then we have the NAR-miner, which uses both semantic constraints and information entropy based ranking. So looking at the results, we are able to see that the semantic constraints reduce rule explosion by around 88%, and the false positive rates on NAR minus 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 in comparison to NAR minus 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 was 90.5 in NAR minus NAR minor minus. So from 99% false positive rate in the baseline, it dropped to 90.5 in the NAR-miner minus version, which sort of has only one of the two novelties, and applying entropy-based ranking further improved the accuracy. 93 out of the top 200 rules were true positives in NAR-miner versus just 2 in NAR-minus, which is the baseline. Now, moving on, a key observation that we saw through the paper was that without semantic constraints, many rules were missed. For example, one of the rules that were missed was the freenet dev and k-free negative correlation was not detected without semantic constraints due to high raw support. And secondly, the information entropy successfully ranked all the relevant rules within the top 200, increasing the true positive rate. And only looking at the comparison with positive rule mining, we were able to see that only 3 out of the 17 bugs were detected by the positive rule mining. And also, of those 12 bugs were still undetected even after applying the semantic constraints, sort of like a positive rule mining minus version. And then negative rule mining finds many bugs that positive rule mining misses, and across all the different systems, right? So this makes us come to the conclusion that it is able to overcome rule explosion and successfully detect overlooked bugs in large-scale systems. And it also is one of the first approaches to mine negative programming rules for bug detection. They briefly discuss the future work where they want to improve ranking and combine it with positive rule mining. That is also one of the things that they discuss about. Thank you for your attention.